each of what the quantum numbers. The first on the list is called the principal quantum numbers. Let us look in or put into consideration the basic facts you need to know concerning the principal quantum number. The principal quantum what number? The principal quantum number is actually denoted with a small letter n. The principal quantum number, please take note of that. The principal quantum number is actually denoted with a small letter what? N. And it happens to be the first quantum number that was discovered. It was discovered in the year 1913 by the chemist known as what? Niels Bohr. Niels Bohr is attributed with the discovery of the principal quantum number, and that took place in the year 1913 from his energy equation, which is given mathematically as En is equals to minus E raised to power 4 m what E divided m E what square divided by 8 pi naught square a square n square. This is what called the Niels Bohr's energy what equation. It was from this particular equation it discovered what is today called the principal quantum number. So please take note of that. Number one, the principal quantum number is denoted by what? Letter what? N, small letter n. Number two, it happens to be the first quantum number that was discovered, and it was discovered in the year 1913 by the chemist known as Niels Bohr from his energy equation given mathematically as N is equals to minus E raised to power 4 mass of E square divided by 8 permittivity square a square n square, where the various symbols as used in the equation have their usual meaning. En simply means the energy possessed by what? The electron in a given energy what? Level, whereas E represents the charge possessed by the electron, which I told you previously is numerically equivalent to 1.6 times 10 raised per minus what? 19 joule. Whereas Me symbolizes or represents the mass of the electron, which is numerically equivalent to 9.11 times 10 raised per minus what? 31 what? Kilogram. Then you have what is called E naught. This is called permittivity of what? A material in what? A free space. The permittivity of a material in a free space is simply defines the ability of what? The material to store electrical potential what? Energy under the influence of an electric what? Field. It is denoted as E naught, and numerically it has a value of 8.854 times 10 raised per minus what? 12 farad per what? Meter. This is the numerical what? Value for what? The permittivity in what? A free space, which I said is the ability of a material or what? A substance to store electrical what? Potential energy under the influence of what? A magnetic field. So please take note of that. That is point number 2 concerning the principal quantum number. Point number 3, take note of it. The principal quantum number principally determines the size of the atomic orbiter. Take note, an atomic orbiter is a region in space around the nucleus of the atom where there is a maximum probability of finding an electron. The size of it could be what? Determined by a particular what? Quantum number known today as the principal quantum number. So under examination condition, they ask you which of the following quantum number determines the size of the atomic orbiter. The answer is the principal quantum what? Number. In fact, the size of an atomic what? Orbiter is directly proportional to the principal quantum number. What does that imply? It implies that what? The higher the principal quantum number, the higher the size or the greater the size of the atomic orbiter. And the smaller the what? The principal quantum number, the smaller will be the size of the atomic what? Orbiter. So take note of that. The size of an atomic orbiter could be predicted or determined with the help of the knowledge of the principal quantum number. Number 4, the energy possessed by the electron in a given atomic orbiter is influenced or determined as well by the principal quantum number. So let me ask you, which of the following quantum number determines the energy possessed by the electron in a given atomic orbiter? It is the principal quantum number. It does that. Yes, listen. The smaller, the higher, listen, the higher the principal quantum number, the higher the principal quantum number, the larger will be the size of the atomic orbiter. And the larger the size of the atomic orbiter, the farther the electron will be away from the nucleus of the atom. And the farther the electron is away from the influence of what the proton that is contained inside of the nucleus of the atom, the lesser energy that will be needed fundamentally to pull it off from the influence of the nuclear charge that is connecting it to the proton that is contained inside of the nucleus of the atom. And this energy is called ionization energy. So please take note of this. When there is high level or the greater the principal quantum number, I'm reiterating on this because it is very consequential, it's very key. The greater the principal quantum number, the larger the size of the atomic orbiter. And the larger the size of the atomic orbiter, the farther is the electron is to the farther the electron is towards the nucleus of the atom. And the farther the electron is from what the nucleus of the atom, the smaller the energy you need to pull it off from the nuclear influence that is pulling it towards the proton that is contained inside of the nucleus. And as a result of that, the lesser amount of ionization energy. On the other hand, the smaller the principal quantum number, the closer will be the electron, or the smaller will be the size of the atomic orbiter. And the smaller the size of the atomic orbiter, the closer will be the electron to the nucleus of the atom. And as the electron gets closer towards the nucleus of the atom, the greater will be the nuclear force of attraction between the electron and the proton that is contained inside of the nucleus of the atom. In this case, greater amount of energy will be needed to pull it off from the influence of the nuclear charge. Hence, the greater the ionization energy. That is one key function performed by the principal quantum number. It determines the energy, specifically the ionization energy, that is needed to actually set an electron free from the nucleus of the atom. Number 5. Number five. The principal quantum number also divides the principal or major energy level, otherwise known as share, into what we call sub Okay, let's look at it from, before I consider that, the principal quantum number can take values that are ranging. Let's consider the values first, or before we consider the values, let me be very specific, that the principal quantum numbers also determines the major principal shares. For instance, when the principal quantum number is equals to 1, it corresponds with a share known as the K share. When the principal quantum number is equals to 2, that will correspond with another share known as the L share. When the principal quantum number is equals to 3, that will correspond with another share known as M share. When the principal quantum number n is equals to 4, that corresponds with the N share. When the principal quantum number is equals to 5, it corresponds with the O share, K, L, M, N, O, and so on and so forth. So yes, the major or the principal share of the atom is equally determined by the principal quantum number. For a principal quantum number of 1, you have the K share. For a principal quantum number of 2, you have the L share. And of course 3, you have the M share, and so on and so forth. The next function performed by the principal quantum number, which is number 6, is that it determines the maximum number of electrons that each of the principal share can actually accommodate. Under examination condition, they may ask you, if the principal quantum number is 2, what is the maximum number of electrons that could be accommodated by the share? For instance, when the principal quantum number is equal to 2, that will correspond with the L share. The question now is, what is the maximum number of electrons that the L share can carry? With the help of the knowledge of the principal quantum number, we can carry out the calculation effectively and of course correctly. By formula, maximum number of electron per share is equals to 2n squared. Take note of that. Where n is called the principal quantum number. That is to say, when principal quantum number is equal to 1, that will correspond with what the K share. So therefore, maximum number of what? Electron for what? K share will give us what? 2n squared. And that is equal to 2 times 1 squared. And that will give us 2 times 1, and that is equal to 2. That is to say, the maximum number of electrons that what the K share can accommodate, which is the share that is closer to the nucleus of the atom, is 2. Going by the formula, maximum number of electrons per share equals to 2n squared, where n is known as the principal quantum number. So you can see, yes, with the help of the knowledge of the principal quantum number, we can determine the maximum number of electrons that each of what the shares can carry. What about if what for a principal quantum number of what n equals to 2? What share does it correspond with? Of course, it corresponds with what the L watt share is called the principal what or major what energy what level. For a principal quantum number of 2, you will have what is called the L watt share. The question is, what is the maximum number of what electron that the L watt share can accommodate? I've given you the formula. Maximum number of what electron is equals to 2n squared. Where n is equals to 2, that becomes what? 2 times 2 squared, and that is equivalent to what? 2 times what? 4. And of course, you have what? 8 electrons. This is the maximum number of what electrons that could be accommodated for the L watt principal share. A summary. Let me just give you a summary. How the principal what quantum number could be used to determine correctly the maximum number of electrons that could be accommodated by the principal or major what energy what level. Let's say this is the principal quantum